Hi everyone. Well, nice to see so many people attending this, even though just by names, there's a nice list there. So as Emmanuel mentioned, I'm coming from Tampere University and my line of research is machine listening. So my presentation touches upon the use of deep learning in the DCASE challenge. So how it is used for audio classification in principle. So I will start by telling a few words about the challenge. Then I will present the basic DNN approach for sound classification. And the way this is used for specifically for acoustic scene classification and for audio tagging. After that, I will very shortly go through the two tasks as they were set up in the 2019 challenge. So the challenge on detection and evaluation of acoustic scenes and events deals with all sorts of topics related to acoustic scene analysis. It was started in 2013 by a number of people from Queen Mary University, including Emmanuel. It's like the gate opener. So it returned then as an annual event starting from 2016. The challenge offers open data and research topics to work on. It practically tries to encourage as much as possible open research and people to kind of join this field. With all this like publication of open data and then the challenge, the number of publications on topics like acoustic scene classification, sound event detection, audio tagging, and so on, it has been growing very, very rapidly in the last 5 years. So during the years, the challenge presented different tasks like acoustic scene classification, sound event detection, audio tagging. These most recent ones, they are also more specialized. So for example, we have had sound event detection and localization, so jointly, or audio captioning, that was this year. So each year we try to offer a nice selection of tasks so that we keep the challenge interesting and the people coming back to it. So you all are aware that since few years ago, the use of deep learning has become quite common also in audio classification. So if we are thinking about the general machine learning approach for classification, this is based on supervised learning, where the set of classes is defined in advance. It requires annotated data for all these classes in order to learn the models. So then the learning happens using algorithms that learn a mapping between the audio in some form, and this usually means that it's represented using some features, and the labels, which are also represented in a suitable way for this algorithm. So this is valid as a machine learning approach for any method. It's not just about the deep learning. The idea in learning is to optimize parameters of the acoustic model in such a way that some measure of the difference between the predicted and the target output will be minimized. So moving to deep learning as a method, if we just think about it, well, we have here a general system architecture. So you can see that the audio goes through feature extraction and the annotation is encoded in a certain way. And then the feature matrix and the target outputs, they are used in the learning process. At the test stage, the audio goes through the same processing to obtain the features. Then the acoustic models will provide the recognition output, which is represented in a similar encoding like in the training stage. So then this kind of encoding can be interpreted in terms of the annotations. So this is disregarding in like completely the actual architecture of the network. This is just what's happening there. So if we think about now about acoustic scene classification, so this is defined as the task of classifying one test recording into one of the predefined classes that will characterize the environment in which this was recorded. So it can be, for example, airport or street or train or park. What this means is that the audio will be given one single label. So this makes it a multi-class single label classification. It's multi-class because we select the label from a set of labels, and it's a single label because we are only giving it one label. So like it's represented in this figure. So what happens in this generic architecture? So we have such that the annotation has only one label for the file. And okay, in this case, this is park. We use what is called one-hot encoding to represent this, which means that the system will have, so the system has as many neurons at the output as the number of classes, and each neuron has one class associated with it. So one-hot encoding means only one of them will have target value 1, and then the rest of them will be 0. These output neurons, then in this case, will use the softmax activation in order to have the situation where the sum of all these outputs will be 1. So the outputs sum up to 1, which means that the classes are mutually exclusive. So when we are doing the test stage, practically we look at the outputs of all the neurons. Ideally, one of them will be close to 1 and the rest of them will be close to 0. So then the neuron which has the maximum activation, that is the one that indicates the classification result. This seems very straightforward. But then if we look, for example, at the audio tagging, so audio tagging, this is defined as the task of assigning a number of labels to the test recording. These labels can be, for example, sounds that are present in the audio. Like in this first case on the left, we have slam and squeak. So here also we have a set of predefined labels, but we can assign multiple labels to the same test file. So this makes it a multi-class, multi-label classification problem. We select from multiple labels and we can select multiple labels. So we can use the same basic structure for the audio tagging system, but with some changes. So one thing is that the annotation in this case will contain more than one label. So when we do the encoding of the annotation, this will be multi-label encoding. It will have value 1 for the classes that are present and 0 for the ones which are not. So then in order to allow multiple neurons to be active in the output layer, we have to use here sigmoid activation function. So this allows independent probabilities for each neuron. Then practically in the output, we may have multiple neurons which are indicating high probability for different classes, which simply means that we might have multiple classes there present. We can just use some threshold to decide which classes we will consider present. So in this example, here there is only 1. Of course, this is a rather simplified view of the modeling. So the system development actually involves selecting feature representations, network architecture, optimizing any possible these kind of thresholds and so on. So this is done using development data. I will go very shortly through these two aspects. So generally with audio, we represent signals in the spectral domain. So I am just assuming everybody is familiar with the spectrogram, which practically gives a good view of the energy of the signal at different frequencies and how this changes in time. So a bit more specialized is the Mel spectrogram, which distributes the information on the Mel scale. So this is simply a mapping of the frequency scale modeled after the human hearing. The Mel spectrogram is most popular feature representation at the moment for any kind of environmental audio classification task. It's really very much used. In combination with some machine learning methods, with deep learning, it can be used to extract some more high-level representations. Then for the network, one very common choice is the convolutional neural network. So in the convolutional network, the consecutive convolution layers allow learning of this kind of a high-level representations, some relevant representations. So the convolution will process the spectrogram in such blocks, which are the kernels or like filters, in order to create this kind of new representation, like the new feature maps. So doing this multiple times allows us to learn the higher level, what we call higher level features. Then, of course, in between the convolution operations, there are also some pooling operations. So those are done for learning, like to allow learning shift invariant features. And then there are some non-linearities. They are implemented in form of rectified linear units. So practically, the choice for the exact network architecture, like number of convolution blocks, size, number of filters, and so on, this is with the developer. Yeah. Now very shortly about the two tasks, how they happened in the DCASE 2019. So the acoustic scene classification task, this was defined exactly like I told. So classify one test recording into one of predefined classes. So here we had 10 classes, like airport and shopping mall and metro station and so on. We gave a data set containing 40 hours of audio. This was a development set. Contained data recorded in different big cities in Europe, including, for example, London, Helsinki, I think Prague, Barcelona. Yeah. So in the evaluation set, we had two cities which were not included in the training set. So this is visible in the lower panel of the figure. Here you can see, like here we calculated the classification accuracy separately on the 10 cities which were seen in the training, and then the other two. So you can see that the orange bar is slightly smaller for all the top 10 submissions for the unseen cities, but they are close enough together. So this means that the systems were able to generalize properly to the problem. Okay, as for methods to solve this problem, a large majority used what I just mentioned. So MEL spectrogram and CNNs. In many cases, the CNNs, they were actually ensemble classifiers. So they are combinations of different systems, different classifiers. So they might use perhaps a slightly different architecture or somewhat different data or representation or slightly differently optimized. But most of the cases were like CNNs. Then the audio tagging task last year, this was a bit different. So it had 80 classes, but the data was given so that there was one very large training data set with unverified labels. So this means that some labels, there might have been completely incorrect. Then there was also a curated training data set in which the labels, they were verified that they were correct, but they might have been incomplete. So this means, for example, that if there is in a file, it could be like it contains sounds of cars and dog, but then only the car is labeled. So when we do this multi-class encoding and we put 0, for example, on the car, sorry, on the dog class, that is not correct. So this is like incomplete, potentially incomplete. Then the test said this was verified to be correct and complete. So for this one also, the preferred approach was based mostly on CNNs and MEL energies, and then a lot of classifiers. But because of this very specific way of the data, it had to contain also some added techniques to estimate kind of the reliability of the labels, because some might have been incorrect. So these two examples, they just show that the approach with this MEL spectrum convolutional networks, it is indeed very general, but a lot of the development must go into the small details. So how the learning process is set up, how the model outputs are interpreted and used. Okay, so this is my last slide, just a very quick conclusion slide. I would say that AI in the form of deep learning has demonstrated high performance in many different audio analysis tasks. So of course here I have only discussed like two specific cases, but there's much more. So there's the speech recognition and so on. So you will hear more today. Of course, for deep learning, it's required usually to have a lot of annotated data, but there are alternatives. There are already also for audio things like pre-trained models that can be adapted for different tasks, or then specific methods that allow learning in a less supervised way. As for the DCASE challenge, so the DCASE challenge offers a good selection of research topics for this environmental sound analysis. The number of participants keeps growing every year, which is very nice. So those of you interested are welcome to participate next year. We don't have yet the tasks, but we will select some by the end of the year, I think. And last but not least, the DCASE workshop was supposed to take place in Tokyo this year, but of course, it will be organized as a virtual event. It will be free of charge, so it might be worth to check out what's going on in there. Thank you.